Good afternoon, everybody. Thank you for joining us on episode 7 from Dispatches from Energy Transition. Got a great episode today, a topic of much interest to me personally, and I think Lucas as well. We're going to talk about the promise of long duration energy storage. Much talked about. There's a lot of alternative technologies coming to market. Long duration energy storage has a unique application. We have some great guests joining us today. I'm Robert Cross. I'm the principal at Outfit. We are the clean tech marketing agency. We focus on B2B technical marketing, animation, visual storytelling for project developers, manufacturers, and service providers. I am joined by my cohort in Dispatches, good friend and colleague for quite some time now, Lucas Miller from Mayfield Renewables. How you doing, Lucas?
Doing well, Robert. Really excited for this one. Appreciate the intro. For those in the audience, my name is Lucas Miller. I'm a senior engineering consultant at Mayfield. Mayfield Renewables is an engineering consultancy. We perform everything from early stage feasibility analyses and modeling all the way through full construction and permitting sets for middle market projects. So with a huge emphasis on microgrids these days, but a lot of commercial and industrial scale solar and solar plus storage projects. And we also do some online education as well. So we're really excited to dig into this topic today. I know long duration energy storage is something that we're hearing a lot about. So really thrilled to have our guests lined up today to learn more about it. So we have our two guests on screen here. I'm going to let both of them introduce themselves, tell us a bit about their professional background. Let's start with Brad Dore from EnerVenue. Brad, thank you so much for joining. Do you want to tell the audience a bit about your background?
Sure. Thanks, Lucas and Robert, for hosting. We're excited to be a part of the webinar with Mayfield Renewables and Outfit. My name is Brad Dore. I'm the VP of Global Marketing for EnerVenue. EnerVenue is a differentiated battery technology. We're going to talk a little bit about what that battery technology means, but I've been with the company now for about 3 years. Really excited, have just excited to see kind of the explosion in the storage market. And prior to that, I've got a decade and a half working in renewable energy on the solar inverter side of the business. So I've seen a lot. I've been on the solar coaster. I've seen the kind of the emergence of storage, and really excited to see where the market and the industry takes us.
Great, thanks, Brad. We're also joined by Jakir Hossain from Storlytics. Jakir, do you want to tell us a little bit about your background?
Sure. Thanks, Lucas and Robert. Really excited to be here. So my name is Jakir Hossain. I'm the co-founding CTO of Storlytics. Personally, my background is in electrical engineering and energy storage and power system modeling. I have over a decade of experience in renewable industry, working with the utilities. And in my current role in Storlytics right now, I'm overseeing the development of the Storlytics software platform, which is basically the industry-leading platform for accurately modeling energy storage projects. So any performance characteristics like degradation, losses, auxiliary load assumptions, anything that is critical for an energy storage projects, that's what you can estimate very accurately in our platform. So really looking forward to the conversation here. The topic here is very close to me, so looking forward to an engaging discussion.
Thanks, Jakir. And I know we've got a few more slides than some previous episodes today, so let's jump right into it. We'll turn it to you here, Jakir. If you can tell us kind of an overview, let's say, of what Storlytics is as a platform, what tools you offer. And maybe let's start with, I see here in your origin story that Storlytics was born out of addressing a clear industry gap. So if you could start by explaining kind of what gap did you see and what led you to found the company to close that gap?
Yeah. So like I said, so both myself and my co-founder, we had a lot of experience in the renewable industry. We started with solar, and as we are transitioning into the energy storage design, what we saw is there is a really gap in a standardized tool for designing energy storage systems, right? So most of the consultant or engineering firms, they were using their own Excel-based tool. And then the OEMs will have their own internal in-house Excel-based tools, but they will not have anything customer-based. So if you are a developer or designer trying to optimize your energy storage projects upfront, there is nothing really that would allow you to do so. So pretty much you are selecting different types of batteries, and even now, based on the cost itself, so dollar per kWh cost, and then the availability and the commercial terms. But that's not really an optimal way for you to design, because if you're not looking into how you plan to use these batteries and then taking that into consideration in your selection of technology and the battery for your project, you're not really making an optimal decision. And it can be pretty significant, as much as like 10 to 15% of your overall project cost. So a lot of tools in the industry, a lot of focus has been given on the revenue optimization. So how you can bid into the market, how you can dispatch it more smartly to get more revenue. But on the cost side, it is still very trivial, very high level assumptions on degradation, performance, 3%, 5% losses, that kind of assumptions, which is not really very accurate, right? So that's where our platform comes into the play. It bridges that gap between your application and your selection of technology, right? So with our platform here, you can simulate each of the different scenarios. You can dispatch your battery, and then you can see which technology or which OEM better fits your need for that particular application. So that allows you to really verify a couple of things, right? First thing, you want to verify that this project that you are designing is going to be able to meet your need throughout the project life. So that's the first validation. Then you want to make sure that from a cost perspective, this is the most optimal one. So you want to also get the cost information based on your technical parameters. So for each of the application, you can run different technologies and make apples to apple comparison. And that is really seamless to the platform. So now you are taking how you will be operating this battery into account as part of your decision making.
Yeah, I think it's really an important point, I think, to emphasize all the different use cases here, right? And we at Mayfield, as an engineering consultancy, we get design projects all the time with entirely different applications and use cases. 99% of the time, the batteries are still lithium ion, or even more specifically, lithium iron phosphate, LFP. And so as the market diversifies, right, how are we modeling energy storage more broadly when we have all this growing range of applications as well? I think that's a really important point.
And one thing I'll add to it, even in the lithium iron phosphate category, you have different kinds of cell coming. So some manufacturers, everybody's making their cell size bigger now. So we started with 280 ampere hour. Now you get to see 500 plus ampere hour. So, and the performance varies between different types of cells as well. And yes, and it's important to capture all that.
And Jakir, what are your typical users look like? Are these mostly developers, end users, more focused on kind of mid-market projects or larger scale projects? Who's typically using the platform?
Yeah, I would say above all, but our primary users are mostly utilities and developers, and both of them uses it a little differently. So for utilities, the different phase of the projects use it differently, right? So initially, when you're starting off a project, your goal is to that, okay, I have this grid need, and I need to put a battery project in here. So what should be the size of my project, right? So that's first question you have. So they will use our tool to identify, based on the particular application, how big of a battery they need. Then as the project move along, you are going to the procurement. Now we have like 5 different suppliers that you are trying to evaluate between, right? So they all are bidding for your projects. You want to do an apples to apples comparison. And being in the industry right now, nothing is standardized on the industry here, right? So every OEM has their own definition of how they define chargeable energy, usable energy, dischargeable energy. There are a lot of nuances attached to it, right? Some will include your auxiliary losses as part of the sizing, some will not include. So it's very difficult to comb through the documents of the proposal and make sure that everything is apples to apples, right? So when you bring everything into a standard platform, it becomes very seamless. So that allows them to choose, look at like which solution is best suited for their particular project and make a very fair comparison. So that's from an utility perspective. And the developers will also do something similar, right? They will also use our platform to accurately predict the solution as well as the cost, right? It's not only your initial capex, it's also the operational cost, right? So one of the characteristics of batteries, especially lithium, is your losses and everything is changing as the battery is aging. So you actually want to look into the overall cost of your projects, your charging losses, your cost for your auxiliaries, take all this into account to have a complete picture. So our platform allows to do that. So they find that very useful. And also a lot of times when you're trying to propose these projects to off-takers, they would often want to see different scenarios, right? What if I do 1.5 cycle, 2 cycle instead of 1 cycle? What happens, like how my sizing changes, how my augmentation schedule changes? All these different questions you're faced with, right? So with the software, good thing is that you can just change a couple of buttons and then basically create a new scenario, and you can very easily now look at what your battery is going to look like if the operating condition changes, right? So that's kind of in a nutshell where some of the users are and how they find it useful.
And in research for this discussion, Jakir, I was going through some literature on the Storlytics website, and you mentioned that Storlytics is a product of collaboration between industry experts and universities. So I'm wondering if you could speak a bit more on how Storlytics collaborates with the public and private sectors, and if there's any overlap there.
Great question. Yeah, I mean, so we initially launched our software in 2021 August, but the research for the product itself started back in 2016-17. So we worked very closely with UNC Charlotte, with their research group there to come up with the main core ideas for that went into the tool, right? And then we still continue to do a lot of close collaboration with UNC Charlotte. Our headquarters is basically very close to the university campus, and we have some close collaboration with the Department of Electrical ECE in UNC Charlotte.
Thank you, Jakir. Brad, it's great to see you today. Long duration energy storage. I mean, there's significant potential with the energy transition. And some broad strokes, talk to me a little bit about EnerVenue and your story.
Yeah, thanks, Robert. To talk about where we're going, it's helpful sometimes to talk about where we've been. And the EnerVenue origin story is really born out of a place that many of the technologies that we use today was born out of, and that's NASA. So NASA developed the core chemistry that we're using, nickel hydrogen technology in the 1970s, applied in the 80s and 90s, and some really high profile applications, including the Mars rover, the Hubble Space Telescope, the International Space Station. So it was a really well-known technology, had millions of cycles, hundreds and thousands of charge and discharges. It was really a robust technology, but like everything that NASA does, it works really well, but it's really expensive, right? So in 2017, just like Storlytics having a connection to academia, EnerVenue has a strong connection with Stanford University. Stanford University, led by Dr. Yi Shui, one of the preeminent material scientists in the world, was looking at existing technologies that we may have overlooked, right? Like he and his team knew that to get where we want to go in terms of the clean energy transition, we're going to need lots of different types of energy storage, short-term, long-term, things that can discharge over a few hours, things that can discharge over a few days. So what are some technologies that exist that we may have overlooked? And they came across the NASA's metal hydrogen design, and they looked at, okay, what can we do to reduce the cost here? They pulled the platinum out of that design, substituted a new metal alloy, and they found that not only could they actually improve the performance NASA's original design. They could do it with identifying a cost profile that could meet or beat lithium ion moving forward. So with that, EnerVenue was spun out of Stanford's Business Accelerator program in 2020. And we've been developing our core vessel technology called energy storage vessels since then. We're designing it with a 30,000 cycle life, designed to essentially cycle continuously through 3 cycles a day for 30 years, right? Really with some improved characteristics around fire safety, around end of life use, around durability. So some really exciting things. Now, today we're commercializing that solution. So we've got pilot projects with utilities and developers, integrators, commercial energy users with our Gen 1 and Gen 2 products. And we're currently working on our 4th generation energy storage vessel, which is the vessel that we'll eventually be coming to scale with.
Great feedback, Brad, and some context. An interesting aspect and something that Drew Gillett mentioned here, long duration energy storage is also an economic term, right? I mean, it's storage in general impacts the cost benefit analysis of projects. What excites you about long duration energy storage yourself?
Yeah, so when you're talking about long duration energy storage, it really spans the gamut, right? You can be talking about, I think, the UK has defined it as 6-hour plus discharges. The Department of Energy in the US looks at 10 hours plus, but we're seeing technologies that run from that 6-hour up to 10, 12, kind of that intermediary bridge up to the really long discharges that can be, tens of hours or hundreds of hours even. So there's really quite a large breadth of potential possibilities out there with long duration energy storage. What excites us is there's a number of applications that fit within those various kind of segments. So I think as we see the storage market evolving, we're going to see different applications that can really utilize that 10-hour discharge, or can really utilize a 12-hour discharge, or the flexibility to charge at 2 and discharge at 10, right? And it really opens up some possibilities in terms of what we're doing on the grid.
It's great to hear. So have you guys identified the sweet spot yet, or do you think it's still early in regard to application as far as when where that sweet spot really hits here?
For EnerVenue, we're seeing a lot of interest in the 8 to 10 hour, the 8 to 10 hour discharge. But again, there's all sorts, and we'll talk about this later as we kind of get into the chemistry and get into some of the use cases. There's applications where you might be discharging it at 2 hours, charging at 2 hours, and then discharging again at 8 hours, right? So that flexibility to mix and match based on the unique needs of your project is something that's quite interesting.
My final question or comment for this slide, my career was actually inspired by NASA, Apollo 11, the moon landing. I'm sure like many other people in the industry, especially some of us that are getting older. Can you talk a little bit about the challenges of commercializing a NASA technology?
Sure. I mean, NASA's known for a lot of technologies that we use today, right? Microprocessors, memory phones, cell phone cameras, things of that nature. So there's a lot of tech that comes out of the aerospace industry. And as I kind of mentioned previously, the big challenge is, how do you commercialize that? How do you take something that's made for space and apply it to a terrestrial application, right? We want to use these things to better improve our grid and improve what we can do with the clean energy transition, and how we can get more renewable energy onto the grid. So, as we kind of take NASA's technology, obviously you're looking at cost reduction. You're looking to really optimize both the cost and the use case for things that we need here, rather than making sure a satellite runs has some different requirements than making sure a data center is able to manage its load profiles correctly. So that's really what we're doing when we talk about commercializing. We're optimizing the design for today's energy users.
That's great. I guess we can kind of segue here, and I know this next slide Mayfield are experts in codes and standards, and Ryan and you have been doing some work around UL 9540A. Why don't we talk a little bit about the properties of the energy storage vessel?
Sure. So and we do call our battery a vessel, right? It's a pressurized vessel. We take our anode and cathode sheets, compress those, you divide it with a separator. That's then hermetically sealed and filled with a water electrolyte solution. So you're not adding additional materials to the vessel over the life of the battery. Essentially, during the charge cycle, the water electrolyte is split into oxygen and hydrogen, and during discharge, that hydrogen recombines with water. So it's a very stable, well-known process that's not prone to the same sort of degradation that you see in other technologies. For example, there's no dendrite formation. It's a different type of battery. And what that does is it gives those unique properties, allows that battery to really be used and abused. There's no risk of thermal runaway. You're talking about a battery that's designed with a 30,000 cycle life. So you're addressing some of these things, as Jakir mentioned, augmentation, and we don't even talk about augmentation. You don't need to augment with our battery. So it kind of changes the dynamic and the discussion around how do you apply these batteries. Ultra low maintenance, there's very little maintenance that's involved with it. So you're not talking about these high operating costs that you had with current technology. I mentioned briefly, the battery is flexible. You can go everything from a 2 to 12-hour charge or discharge cycle, and you can actually do that with a high round trip efficiency, which is pretty unique out of this sort of technology. So it gives, again, the battery owners and the users the ability to really customize and opens up a whole new world of possibilities in terms of how they can apply that technology. There's no lithium, so it's we avoid some of those challenges on the material side, and the unit is highly recyclable. So there's a really a lot of new interesting ways that the technology can be applied and used based on its chemistry.
I think this is an interesting comment, and I'll let Lucas kind of take over. Maybe Jakir, you can kind of weigh in on this as well. From a project development perspective, batteries, energy storage, it really gets into that balance too, right? Between CapEx and OpEx. Kind of curious of both of your vantage points in regard to that, because given long duration, product life cycle, it really gets interesting from a project development vantage point.
Yeah, I think I'll mention something and then maybe hand it over to Jakir on this one. The ultimate measure of battery is the cost per cycle, right? And what does that battery cost to run per cycle? And so although CapEx is important, right, we're really kind of changing the game on the OpEx side of the business, and that's where you really need somebody like a Storlytics to come in and kind of model that technology to show, we're not just doing a single 2-hour discharge or a single 4-hour discharge. But we may be doing 2 cycles a day, and you might be doing that over a 20, 30-year period. So what does that do to your levelized cost of storage? And again, that's where that modeling, Jakir, you can talk a little bit about the modeling that Storlytics does and how they can kind of take those unique concepts and turn that into something that's digestible.
Right, absolutely. Yeah, I mean, you hit the nail on the head here. So like I was saying also before, that it's really important to take a look at those use cases. So if you have that kind of use case where you're doing 2 cycles per day, if you give that to a lithium system now, even though the degradation has improved quite a bit, but still they will degrade quite more compared to, in this case, EnerVenue, right? And then there are also other aspects to it, right? So if you're cycling it more, that basically means your battery is not sitting idle that much, right? So if you have a technology that is self-discharging more, so basically cycling it more is advantageous for that kind of technology, right? So really depends on how you are using the battery, and to be able to do modeling that can capture all these physical characteristics like self-discharge, losses, degradation. And then you can accurately project what your project OpEx are going to be in the, as over its lifetime, right? And instead of making the call based on, so something might look more expensive just based on dollar per kWh today doesn't necessarily mean over the 20-year project life, that's going to be the most expensive solution. So you really need to look at the overall project life cost rather than just the cost of the technology today.
And along the lines of modeling and the complexities of different use cases, we did get a question from the audience for you, Brad. How big are these vessels? So what is the megawatt and megawatt hour rated capacity of the vessel units? And then maybe after that, Jakir, I'd love to hear from a modeling perspective, what are the key inputs that you're looking for when you are modeling a long duration technology? So maybe let's start with you, Brad, on some specifics of this unit, and then I'd love to turn it to you, Jakir.
Sure. So the vessels are 3 kilowatt hours, and essentially what we do is these can be applied in a number of different ways. We're deploying them in an energy rack, which is a 150 kilowatt hour DC block, and there's really, they can be scaled. So these things can go from very small systems all the way up to hundreds of megawatt hours. That's not really a challenge. It's a very scalable technology. We've actually even found a way to take our energy racks and stack them, so we can stack these things 2-3 rows high into what we call an energy venue. So it's really a great building block for both commercial and industrial and grid scale energy storage.
Yeah, and then to the other part, the second part of the question, Lucas, you asked about what are the things we need to consider when creating these models, right? So the most important thing is to make sure that you are capturing all the key characteristics of energy storage system, right, from a grid perspective. So those are being degradation, losses, round-trip efficiency losses, your self-discharge, any kind of rack balance imbalances that happen as you stack up these systems, right? So those are some of the key things that you'll look at, and also the mechanism for it, right? So some systems can have only energy degradation. Some can have both energy and power, both degradation, right? So understand that. Some technologies, the degradation is only affected by throughput. Others, it can be affected by throughput, your state of charge, your depth of discharge, your C rate, temperature, a lot of other factors, right? So understanding the core of the technology and how it basically gets impacted, all these different parameters, and then translate that into a model that can accurately capture is the key work that needs to be done here.
Thank you, Jakir. I just have another question from a manufacturing perspective. Brad, one of the things that is interesting to me about the energy vessel, it's from a manufacturing vantage point, on-site generation, how it fits and slots in. Can you talk a little bit about just the flexibility of the vessel from a product development perspective, and where it can go and where it can situate?
Sure. I think we can actually transition to the next slide. That we've got a couple examples here that make sense. So EnerVenue is taking this technology to market primarily on the large scale side, in grid scale and the C&I space. We do see an application for it in the residential space as well, but today our focus is on large scale. And when we're looking at that commercial and industrial segment, we've got a concept called building integrated energy storage, where you're taking these vessels and you're integrating them into spaces that might not normally, you might not think you can put battery storage in. You think attics and basements and empty warehousing, places that are essentially just being wasted. And we can turn that unused real estate asset into a power plant, essentially, where you're storing and using energy. And that's really unique. You're not necessarily needing to plunk down batteries in the middle of your parking lot. You can reduce your footprint in terms of where your energy storage goes. And although conceptually, we've yet to realize some of these projects, we've got some folks that are really on the cutting edge of what can we do with this? Can we build this into the exterior cladding of our commercial building? And so we've got some really unique concepts around, if you had a battery that had that really improved fire safety, if you had a battery that could cycle 30,000 times and had very little maintenance, could you put it in places that would be maybe a little harder to access? And so, again, some really unique concepts around that.
Yeah, and I think when you say building an integrated energy storage, I'm sure our audience's ears all perked up at the same time. And we got a few questions in advance with regard to fire safety. We've looked a little bit at the thermal runaway risks for this metal hydrogen battery, Brad. This is something that we at Mayfield have done a ton of research on in the last year or so. We're going to publish a course on UL 9540A next week. But a lot of this research is mostly focused on lithium ion technology. That's most of what's getting deployed today. All lithium ion cells commercially available do go into thermal runaway. Their off gases are flammable, so there's not only fire, there's explosion risk associated with them. And I think that leads people to believe then that that's true for all energy storage, when that may or may not actually be the case. So if you could speak a bit more around battery fire safety for the metal hydrogen units in particular, and what is it about these that maybe reduces the risk or negates the risk entirely of thermal runaway?
Yeah, so I can talk about it at a high level from a chemistry standpoint. When you're talking about thermal runaway, when our vessel heats, when the EnerVenue vessel heats, two things happen. As we talked about that the chemistry earlier, that hydrogen recombines with water. So as that vessel heats and reaches a certain point, two things happen. One, it vents. But the great thing is it's venting water vapor. So even if you overcharge this thing and you're pushing it beyond its limits, and you're heating up a battery, or we've done the burn pit test where you put the vessel over a fire pit and you heat it up, you're gonna vent, but you're also gonna vent water vapor. So that's a pretty, if I'm gonna take if my battery vessel has to vent something, water vapor in the event of a fire is great, right? Now there are building codes around hydrogen. There is hydrogen within the vessel, so you do need some proper venting. But again, one of the interesting things about hydrogen, it's lighter than air and it rises about 45 miles an hour, so disperses very quickly. And when you talk about fire safety, you need a couple things. You need fuel and you need an ignition source. So if you're not pushing this thing into thermal runaway, you don't have that fuel. There's no ignition source. So you're really talking about a much safer type of chemistry. That is, unless you're talking about a meteor hitting a building, in which case, I don't think there's a battery technology on the planet that's going to be fire safe under that instance. But really,
Hey,
EnerVenue's model.
Brad,
Yeah.
we can't talk about that stuff going on in New Jersey right now.
Yeah. Okay. Yeah, EnerVenue's model really improves on the what's currently available out there.
I mean, it's a NASA technology, right? It could be meteor proof.
I guess it could be. We're not going to warranty against meteor strikes, though, guys.
We did get a good audience question here from Matthew. This one for you, Brad. Metal hydrogen batteries have high energy density, right? I know this isn't the topic for today, but are you also contemplating other use cases like transportation?
So I'd actually say we're the opposite. We're not as dense as what you'd see out of batteries that are like the lithium ion that are going to be used in transportation applications. And so that's where we're really focused on the stationary storage market. Because the energy density isn't the same, we're not going to take a look at the transportation play. But what we've also done, as I mentioned earlier, with our energy rack and the ability to stack that 2 and 3 level highs, we've developed a way where you can actually, despite being less dense than lithium ion, we can fit within an acre, as much or even more than some of those technologies that are out there that are deploying containers. And because you have that improved fire safety, there's some latitude around being able to do that. So no, electric vehicles are not in our plans, but certainly providing capacity for electrical vehicle charging on site, that would be something that you'd apply with an EnerVenue technology.
And on that note of energy density, I'm going to go back actually one more slide. When I think of long duration storage, one of the primary examples that comes to mind is flow batteries,
Mhm.
which can decouple their power from energy ratings, right? So if you need more energy, you get an extra tank of electrolyte, and now your battery went from 8 hours to 12 hours. That's making some physical changes to the system to change its performance characteristics. It sounds like in the case of metal hydrogen here, could I assume that I have one vessel unit, and that unit without modifications could go from a 2-hour to a 12-hour discharge?
That's correct. Yeah, we're not. We're not adding anything to the battery over time. It's but the characteristics the battery again can do from anywhere from a 2 to 12-hour discharge. So we fit kind of in that bridge from what's available today in terms of 2 and 4 hours, or what's economically viable today, the 2 to 4 hours, bridging up to other technologies that are out there that might have discharges in the hundreds of hours. And again, each of these kind of has a unique application, and there's a sweet spot for each one of these technologies out there. And that's really the exciting thing as we move through the clean energy transition, is we get to see, all of these different technologies provide some value. And again, we're fitting in that space that we think has a high value for a lot of commercial and industrial and grid scale energy users.
I think this is a good time to open up a brief discussion to the group here. Part of dispatches is to have a conversation. There's a lot happening in our industry. I have a question from Ken Hoffman, sales engineer from ESS. Both Lucas and I are pretty familiar with ESS. We both live in Oregon in different parts. ESS has iron flow batteries. Ken's question: what do you feel is the greatest obstacle that LDES systems have to overcome to gain market share? And then especially when competing with lithium ion. I'll kind of open up to the four of us, or even the audience, because I think that's a really big topic. Go ahead, Lucas. What do you think?
I can jump in with a couple things here. Just right off the top of my head, there's two things in order for LDES technologies to gain market share that need to happen. One, they need to deliver on the promise of the technology. So there's a lot of companies that have been working in developing technology, and number one, they've got to deliver. Two, it needs to be at a price point that makes sense. So certainly, there are CapEx considerations, but this is really about understanding and changing the dialogue and the narrative from a CapEx discussion to, a LCOS discussion, and what is the cost of that energy over time. And some of that is, again, using folks like Storlytics to model that technology and show the value in that sort of use case. If you guys have other. Yeah, sorry, three. The one thing that I think we're starting to see now is policy support. There's a 2 and 4 hour market today that's economically viable, but we're starting to see a number of locations, across the globe. There's state requirements they're starting to look at longer duration and how can we support, policy mechanisms that assist in getting that technology up to scale.
Thanks, Brett. I'm going to kind of point or pivot to Jakir on the same question. My background prior to energy was economic development and financing. So I would think like Storlytics tool, what role does economic modeling have, particularly from understanding the financing, underwriting? Do you see that being a really big aspect for LDES applications?
Yeah, I mean, I really think like one of the key enablers for the LDES is gonna be to, do financing for these projects, right? And to get financing, you basically need market access and then long-term visibility, right? And that basically gonna come, you have to create those markets, and that's gonna be really part from the integrated resource planning of different utilities that they do, right? So part of their planning, these LDES technologies needs to be part of their planning upfront, right? So now, yeah, 4 hours is where the market is at for energy storage, but you need to add 8 hours, 10 hours plus, even 100 hours, that kind of technology as your resource mix, so that when you're doing the planning, depending on your grid conditions, you have the options to choose from these technologies. right? And that's really going to open up the market for these technologies, where now there is going to be an incentive to build these technologies because there is a need for these things.
Yeah, I think that's a great transition, Jakir, to what we wanted to really spend some time on here is some applications for long duration storage. We've got 3 total, 1 starting here on the utility scale, and then 2 more for commercial industrial applications. But I'll give the floor to you, Jakir, if you want to walk us through. It was really exciting, I think, to learn about this gap that you guys have found and how you started to address it. If you want to walk us through what's on the slide here.
Yeah, sure. So to piggyback on what I mentioned earlier, is that so there is this gap that you need to have these resource mixes of long duration storage of different durations to be able to select them as part of your integrated resource plan. So right now, what we see is that basically what is integrated resource planning? A little bit of background, right? So most utilities here looks at 5, 10, 15 years in the horizon and trying to see how they can meet their load growth and other requirements, right? And they have to have different types of resources to choose from. They have either natural gas, nuclear, and a solar, wind, energy storage, and all that. So when it comes to energy storage, most of the time it's defined around what is economically viable today, right? Lithium, 4-hour, 1 cycle per day, 5 to 88% round trip efficiency. That's what gets defined, right? So when you're running these models, by default, it is only looking for areas where you need a 4-hour solution, and then trying to pick your how much of energy storage you will need, right? So that's really not optimal because you are not including LDES as part of your planning. So obviously that's not coming out as part of your resource plan. So instead of that, what you really should be doing is modeling these LDES technologies more accurately to understand where these technologies excels, right? And then identify their use case. So like maybe for EnerVenue, right? So we know they can do a lot of high cycling. So definitely for a high cycling application is going to be best suited, right? So for an EnerVenue technology, you don't need a 1 cycle per day limitation. You can have 2 cycle or even maybe 3 cycle or 2.5 cycle, depends on your duration. So you can have that. You can basically characterize your LDES technologies based on where they basically excel. And then step 3, now you can have these different models. You don't have only energy storage for 4-hour. You can have energy storage model for 8-hour, 12 hours, 20 hours, a lot of different buckets. And then you run your model, and then the output of your model is going to be, we need maybe 5 gigawatt-hour of 4-hour duration, 2 gigawatt-hour of 8-hour duration, 1 gigawatt-hour of 20-hour duration, right? So you can get that kind of requirement. And now that opens up the market for you. So now these utilities will try to procure these assets. And by default, their requirement is going to be, I need an 8-hour plus technology, right? So that's when developers and all get into this, and it's going to streamline the advancement of LDES at that point.
So Jakir, is the default here 4-hour storage strictly because lithium ion has become so dominant and the performance characteristics of it lend it to be a 4-hour, 2 to 4 hour, let's say, battery? Or is there more to it than that?
It's pretty much that. That's like pretty much every system that you see is around 4-hour, and that's where it's economically is more optimal in that range. It's trying to push even beyond 4-hour, but still 4-hour is the most dominant, is what I see. And then 365 cycles a year, 1 cycles per day. Those are is the limitations that's mostly prevalent. So most utilities in their resource planning use that as the definition of energy storage.
Got it. And when you're modeling long duration, especially, are you making bespoke models for specific products like the EnerVenue vessel? Is there like a catalog, let's say, of specific technologies with model numbers like one might find in Helioscope, let's say, or are users prompted to enter certain characteristics from a battery when performing a model?
We have a battery model library, which contains both lithium as well as non-lithium technologies. So we have a handful of non-lithium technologies like long-duration energy storage in our model library as well. So the user doesn't need to build one if they can choose one that from our model libraries. But we also give the flexibility, right? So we have a model construction guide. If you're working with some model that is not there in our platform, you can create your own model very easily by following the guide. So.
Great. And one more quick one for you, Jakir, then we'll move on to some commercial industrial scale applications. What are some concrete steps if we have some utility scale storage developers in the audience? What steps can they take to improve this IRP process?
Yeah, so the IRPs are mostly run by the utilities as part of the resource planning or the ISOs, right? So for them, it's more about understanding the technology. So what is out there, right? What are these LDES technologies are capable of doing? Understanding that and then basically modeling that as an option in their IRP tool is basically the right way to go about it. Right now, these tools are not aware of what all these LDSs can do, right? Everything is based on kind of lithium and where lithium shines. So it's going to be important to change that and make these LDS solutions as part of their modeling process.
Great. And speaking of seeing what these technologies can do, let's take a look at, we've got two more examples here. Brad, I'll turn it to you here to walk us through this first one, looking at data centers.
Sure. So I think everybody's, we've been hearing about data centers so frequently in the media now. I mean, raise your hand if you haven't read an article about the energy demands of data centers in the last 2 or 3 days, right? We know that between the data center boom and the energy demand that's being driven by AI technologies, that this is a spot that's ripe for energy storage. There's 11,000 data centers worldwide, and data centers account today for about 4% of global energy consumption. And that consumption increased by 55% in 23 over 2022. So this is an accelerating and increasing market. Now it's expected to double to almost $2.24 billion by 2030. You've heard Microsoft, Google, Amazon, they've all invested in different types of technologies, renewable energy storage to help fuel kind of those data center needs. And the next generation data center doesn't necessarily look like the data center of old. This isn't a pure resiliency play anymore. It's not just backup. Certainly that's important, but they're looking to reduce demand charges. They're looking to lower costs, to integrate renewable energy. Sometimes that energy is that storage or that on-site energy is the key to being able to site a data center application. So there's a lot of new things around data centers that we're seeing that's really exciting for the renewable energy and the storage industry. If we go to the next slide, we can actually take a look at one of the use cases that we've talked to folks about in terms of how they apply kind of that flexible or that LDES technology. So as I mentioned earlier, this is one use case that's outside of resiliency. Your discharging is needed to reduce peak demand, or you're optimizing the time of use rates. Data centers have large, oftentimes consistent loads, which allows you for longer duration planning to address that consistent discharge. So as we mentioned, using storage, you can mitigate those load requirements or frankly, the unavailability of transmission power from the grid with the longer duration storage. Allows you to integrate that renewable energy, reduction of your energy costs, while also reducing your carbon emissions, right? So one of the big concerns that we're seeing with data centers is all this demand, is it going to create demand for more natural gas plants, right? And how do utilities and how do commercial entities deal with still being able to meet their carbon reduction requirements and their carbon reduction goals while facing this demand? So storage again fits into a place where that might be the key again, that unlocks the ability to site a location. Here we show a discharge during a startup. You're supplementing your power from on-site solar during the day. You're discharging to reduce peak demands. And so you can do that again over a long period of time based on the needs of that individual data center.
Brad, thanks for that. I'm going to give a little bit of a dispatches tease. We will be having a big event next year in regards to data centers, AI, things of that ilk. I'm not going to go beyond that for the moment. And yeah, there's a lot going on. Kind of curious from Jakir's perspective in regard to modeling. There's mixed energy use cases, right? And complexity. What do you think, again, kind of the role and simplifying things from the software perspective?
Yeah, I mean, there are a lot of ways. So yeah, so it's important to look at the charging discharging pattern like you have on the screen. If you just say it 1 cycle per day, there are a lot of ways you can do it 1 cycle per day, right? So you can either do from 100% state of charge to 0% state of charge, or you can do like maybe 2 times. You're going from 75% to 25%, and then doing that again, right? So from a cycle perspective, throughput perspective, both are same. But from a degradation or performance impact perspective, both are not same, right? You have different resting period for both of that scenario. You have one scenario with higher depth of discharge impacting your degradation more compared to the lower depth of discharge, right? So exactly how you are using it and taking that profile is critical for you to do any kind of assessment. If you are making 1 cycle a day, 2 cycle a day, that's good for high level estimate. But as you are trying to hone down and get into the higher level of accuracy of your project design, you need to look into those nuances about how this cycle's actually going to look.
Thanks for that, Jakir. Brad, I have a question for you. I think you spoke to it a bit on the front end from Bayo, where is EnerVenue in the market? I mean, you're in the market. And if not, what's the timeline from your vantage point on the C&I piece?
Yeah, so I mean, I'd definitely say we're in the market. We've shipped Gen 1 and Gen 2 product, but I should also say that, you know, we've been capacity constrained and we are selective with kind of our customer engagement. So we've really been smart about, you know, how we're going to market and kind of the technology that we're using, and we're learning in each one of those revisions and implementing additional changes. You know, for example, we learned a lot with our BMS moving from our Gen 1 to Gen 2. Now, again, making the decision to move to Gen 4 and skip a product generation, you know, delayed our scale plans a bit. But ultimately, we're ending up with a energy storage vessel with more power, more energy, greater energy density, and a better overall offering to the end user. So that Gen 4, as I think mentioned earlier, you know, we're proving out the manufacturability of that line right now. And once that's complete, you know, we'll be looking at producing at scale. And so we are actively engaged with key customers and selective customers on their pipelines and projects. And those discussions, you know, we've been having those for quite some time now. So hopefully that answers the question. Yeah.
See, we're getting close to the top of the hour here. We do have one more application for you to walk us through here, Brad. Now we're looking not data centers per se, but now more so industrial microgrids. So larger commercial scale facilities that may or may not be connected to the larger grid.
Yeah. So when we're talking about commercial and industrial, you know, one of the things that we're seeing is a large uptick in interest from traditional oil and gas players that are looking to, you know, decarbonize their operations. And so, you know, if you look at just the oil and gas market, accounts for 9% of all global CO2 emissions on its own. Mining is responsible for a huge percentage of the world's annual electrical consumption. So when you're just talking about, you know, the mining and the industrial sector, you know, they've got strong carbon reduction goals and requirements to install renewable energy, and certainly storage is a way that can be done. They're one of the folks out there that really understands the long-term asset value that a vessel, an energy vessel that can, you know, do 30,000 cycles can bring. They understand what it's like to have with those maintenance requirements, how important those can be. And so, we're really interested in engaging with these folks. We've had a lot of interest on the mining and industrial and commercial side, because there's so much need for it. When you talk about microgrids and eliminating unpredictable fuel costs, implementing these at a mining site, you can lower your fuel consumption costs. You can lower your fuel transportation related costs. It's less O&M. It's less complexity. You're reducing your carbon emissions to meet your organizational goals, your policy requirements. That longer dispatch allows for really dependable operations. So it's really an excellent fit when you talk about things like mining, hospitals, universities, critical government infrastructure. If we take a look at the next slide, we've got a kind of a use case here that shows what a microgrid supplying morning and evening power might look like, and it's a battery use case, charging from the grid or diesel overnight into the early morning. The site discharges energy to assist with the morning startup. The discharge is just long enough to handle those morning loads. Then those batteries are charged with solar or grid power, or even supplemented with diesel. And then they discharge over a longer period, in this case, 7 hours, to support a long afternoon peak and evening requirements. So you see that flexibility, the ability to cycle a relatively short period in the morning, charge, and then discharge over a longer period in the afternoon. Now, of course, this use case is highly dependent on a number of variables, but it shows kind of that flexible energy storage and how that can be used to short and long durations, as well as how solar or on-site renewable energy can be integrated with grid power and diesel gen sets, and providing really a lot of flexibility in those use cases.
Great, thank you, Brad. Yeah, I personally really like seeing that the state of charge, the discharge charts here are really helpful, I think, to visualize the major differences in just these two applications we've seen, but you could easily imagine one where maybe you're discharging 4 times a day. It's no longer cycling once or twice, but many, many times, even for shorter spurts. Really opens a lot of doors up for potential projects. We always close out these episodes just kind of distilling down what we've talked about, a few key takeaways. We've got a couple minutes left, so if you're in the audience and have any questions, now's a great time to add those to the Q&A tab. To break down what we've looked at, first, we want to encourage you to look beyond traditional lithium-ion energy storage options, particularly at that IRP stage that Jakir walked us through. So we have more options available to us today than just lithium-ion, specifically just LFP. It's important that we start to bake that into our modeling and procurement. Along those same lines, this long duration energy storage category is really an umbrella term that includes a ton of sub-chemistries and technologies underneath it. So all the way from pumped hydro, where you're moving water from a low reservoir up to a reservoir on a hill, and now gravity is bringing it back down and returning a turbine, to the metal hydrogen technologies we've looked at today, and even flow batteries. So if you hear long duration, don't attach it to one particular type of energy storage. There's really many that could fall into that category. And then thirdly, modeling degradation that is specific to your use case. So we just looked at 2 different discharge charts. You can imagine that those batteries may degrade at different rates, and whether you're cycling once a day, twice a day, 4 times a day, that may impact what your battery looks like 10 or 20 years down the line. So it's important to bake in what specifically you're going to be using your battery for into your models, and then including degradation in those. I'll open it up to Brad, Jakir, Robert. Anything else that you guys want to add to this list here, or close out and let our audience know?
I think one comment that's pretty important with the industry, particularly given complex projects, is the importance of collaboration between hardware and software and integrated systems. And this stuff is pretty complex. And we appreciate EnerVenue and Storlytics coming on today, in part to help explain the complexity. That's pretty cool.
Great. Well, we've got some contact information on screen. Maybe let's start with you, Brad. Can you tell folks just how can they get in touch with you and EnerVenue or learn more about the product?
Sure. Yeah. I mean, definitely a couple ways. You've got my email there. If there's additional dialogue you'd like to have, feel free to reach out to me directly. I'd also encourage you to follow us on LinkedIn, and then you can always visit us at enervenue.com.
Yep.
Great.
And for us, same thing. If you have any particular question or follow-up regarding the topic we discussed, feel free to shoot me a direct email. You have my email address in the screen here. And then you can follow us on our LinkedIn page, and then you can visit to our website. And if you want to take a look at the demo of our software, you can book a demo from our website. And we also offer 14 days free trial. So all the options are available for you.
The final note as we're kind of closing out the year, dispatches has been renewed for a year or two. We are very appreciative of our partner at Solar Builder and pretty excited to make some announcements in January when we all get back from the holiday break. Brad and Jakir, thank you for joining today. Lucas, I've enjoyed doing this with you. We'll take a little break for the holidays, maybe a couple days.
Yeah, thanks.
Great.
Thanks for hosting this. We appreciate it.
Thanks for having us. Thank you.
Thanks, everyone.
Thank you.